Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is the final one in the series on circular motion, constant angular speed, and it focuses on motion on a sloping surface. Well, what do we have in mind? Watch this experiment. That's what we have in mind, where the motion of the speed of the particle seems somehow to stop it dropping as you would expect it to under gravity. Here's another instance of the same thing. You have cars on a banked track. Is there a tendency to slide upwards or downwards, or is it possible to choose the speed so that the car travels without friction at the same horizontal level? These are the problems to be analysed in this particular section. You'll be aware that banking is used for this sort of exercise and for cycles as well, in order to create a situation where the bends can be taken faster than would otherwise be possible. Let's take a first example. A car travels around a bend with radius 300 meters on a road banked at 15 degrees. We're to find the speed of the car if there's no tendency to slip. Well, there are two diagrams there. The one on the right simply represents the idealization of the bend. That is a full circle, even if it doesn't actually do the whole circle. And we've got the velocity shown on that diagram, and that's what we're going to be trying to find. Well, the magnitude of it, which is the speed. Now, the force diagram has the reaction from the road surface, which is shown perpendicular to the road surface, and we've got the weight shown downwards. You would expect normally in that circumstance to have a force parallel to the surface, which would be friction. Certainly if there were no acceleration showing, you would need a third force for equilibrium. But in this particular case, because there's no tendency to slide up or down, we don't need friction for equilibrium. So the model idealizes it by saying there's only the normal reaction and the vertical weight. And then the acceleration is accounted for by the imbalance between those forces as vectors, and that gives the acceleration to the center using Newton's second law. So let's attempt some calculations on the basis of this, exactly the same diagrams. First of all, we resolve vertically on the force diagram, so we can balance the vertical component of R against the mg downwards. Then we have the horizontal component. This time it will involve the acceleration. There'll be a component of R shown by R sine 15, and that will be equal to the mass times the acceleration. We're not told the mass, so I've used the letter m for the mass of the car, idealized here as a particle. The third equation we'll get by working with these two. We can see that the m cancels, so if we divide the second by the first, the r's also cancel and we get tan 15, and we're left with the expression which derives from the acceleration and from the contribution of gravity through g, and that's all. So that's an equation for v squared, which we can solve and then take the square root. Now v could be positive or negative, which means that essentially the problem relates to a car that's coming out of the picture towards us or into it. The analysis will be exactly the same. So when we fed the numbers into the calculator, we get the answer, which we can now give in context with the units. So our speed is 28.1 meters per second to one decimal place. Now we'll consider now what happens if you go faster or slower. If you go faster, the acceleration term is going to, which appears here, is going to have a bigger v. So somehow or other we're going to have to generate that greater acceleration. Now, you couldn't do it with an r which is determined by the way it balances mg. There must be a contribution to something else. So if you need a bigger force along the radius, it can only come from a force which is downwards. Now that will be seen in the next diagram, where we're asking the question what happens if it travels faster. Well, we've just argued that there must be a force downwards. Now there it is, and that will be contributed by friction. If on the other hand it travels more slowly, then we're going to get a setup in which the v squared over r term is rather less, and so it isn't enough to match the r component, and that means to say there must be a force reducing the effect of r along the radius, and that can only happen if it's up the plane. So there we are, we have a friction force up the plane. Now that, looking at those two together, if we go to the previous slide, that tells us that if it's going faster, there's a tendency to slide up, which friction has to stop. And if it's going slower, there's a tendency to slide downwards, which friction has to stop. So that corresponds to intuition. That brings an end to this particular video on the sloping surface motion, and also to the series on constant angular speed. The next section, which will be circular motion 2, looks at problems where the circle of motion is in the vertical plane. I hope to be with you later to explore that.